statistical scale invariance in turbulent flow. In particular, this relates to the phenomenon that we coined intermittency. And it also relates to the notion of steady-state turbulence. So just to remind you of some of the subjects we discussed last week, essentially we were dealing with the Navier-Stokes equation. With forcing and dissipation and dissipation, incompressibility, and we argued that in the limit when u goes to 0, u is essentially can be described as a stochastic process. With certain property. And in particular, we discussed the K41 framework. We're stating that in the limit of u goes to 0, statistical symmetries hold for u. In particular, rotation, translation in space and in time, and scale invariance. All for you. And we argued that this K41 a structural function, to a certain power p. Then we é mute? E agora? É melhor? Ah, perfeito. All right. So, yes, what I was saying is that we argued that the K41 framework was implying the existence of a scaling range. So that basically, for L between small time and large time, and small scale and large scale, we should expect that any average of increment, which represents some kind of a gradient at a scale L, should scale as L to the power P to H0, with H0 equal 1/3. Now, what we argued is that this picture is certainly not true, not observed. That instead, if we were to plot what we define as the scaling exponent, which are the logarithm, the limit, as L goes to 0, the logarithm of this guy divided by log of L. Then we see, so this would be K41. P over 3, so that that's P equals 3, and that would be 1. And instead, what we see is something which is a bit curved, observation. The question is, how come? And we argued at the very end that we could propose a very heuristic scenario, so that a heuristic scenario, which we labeled the random H model, that if we assume that the scaling exponent is not deterministic, but rather given by a distribution, scaling exponent H is a certain normal distribution, say mu and sigma, then we can reproduce the observation. The problem is that this model is like a rabbit that is taken out of a hat. Okay? So in particular, it is absolutely not clear what are the connections to the LS equation. Okay. So in fact, the connection between intermittency versus NS, it's a complicated subject, and probably it will be discussed at some point in the weeks to come, probably starting next week by Alexei. So see next week. And today, I just want to introduce another layer of model. So to discuss, in a sense, a simpler problem than the Navier-Stokes equation. And this today, so a simpler model, where we can make we will be able to make a connection between the presence of this kind of scaling variance and the underlying equation. And this model that I want to discuss today, so today, is the same title, except that we are going to add a word, in the word passive. Today, passive scalar turbulence. So, what is a passive scalar? So let me just first begin with some basic facts. So just for the sake of fitness, the resources for this course will be biblio. What is a review paper by Barhaft from 2000. And also some lecture notes by Galetsky. Okay, lecture notes. I think it's 2000. It's non-equilibrium static and turbulence. So Christoph Galetsky passed away 2 weeks ago, but his ideas, I think, are very much alive, and this I want to discuss. So, a scalar what is a scalar? So, suppose a scalar equation, so a scalar, it's a scalar field, theta of x, t, okay, where x says, okay, we are going to take it in torus without loss of generality, and t is given an interval. And it will describe, the idea is that such a quantity will describe a variation of temperature, or just a temperature, it says. Let's be simple. Temperature, concentration field, concentration, etc. And he said this is the kind of what it has to be thought about, which satisfied the scalar equation, d over dt of theta plus u dot theta equal some right-hand side. So this is, on the right-hand side, there is a scalar source. And a diffusive term. And of course, there is this u here. Okay? And u, it's a prescribed realization of a velocity field. Okay. So the easy interpretation of this equation is the following. So let us first take the diffusive term and the source equal to 0. Then the Scalar equation describes a conservation law along trajectories. Describes the conservation of the scalar along Lagrangian trajectories. Of the velocity field u. The velocity field u. So what I mean by that, so suppose we have to define what we mean by a Lagrangian trajectory. So Lagrangian trajectory it is just something that it's something that we will call it's the position at time t of a particle which was at time t0 at position x0. And so which satisfies the equation dx over dt equal u of xt with the initial condition x at t0 equal x0. Okay? And so, forgot. I need to supplement this equation say, with an initial condition. So this is the equation that is solved by the scalar, and with initial condition, which will be theta of x times t equals 0 equal to theta 0 of x. Okay. So now, this equation simply means that the initial data is conserved along Lagrangian trajectories. So Lagrangian trajectories, which is defined by this equation, so you have something like that. So you have at a certain moment of time, you are at x0, t0. At another moment, you are at x, t, x0, t0. Okay? And this simply means that so means that theta of x t x0 t0 at time t equal theta of x0 t0 for all t. Okay. This quantity is conserved along Lagrangian trajectories. And maybe it's, so because if we formulate this problem as an initial value problem, let us just switch notation. I have called this x0 t0, but I could call this x and t. And so x and t. And this I will call S. And this I will call S. Okay, and this is x and t. And say we take s equals 0 here. So we take s equals 0 means that theta of x times 0, knowing that there was an xt at 0, is theta of xt. Looks ugly. So what is this guy? It is the value of the scalar at initial time. So it is nothing but theta 0, the initial data. And this is, so this is nothing but theta 0 of x 0 xt. And this is theta of xt. So to just illustrate this formula, for the sake of illustration, so we have, say, time going there. This is the time t goes 0, x. So if I want to know the value of the scalar at this position, x and t, okay, I just have to trace back in time the fluid trajectories, the fluid trajectory which is at this position at time t. Poof. And this is theta 0 of x 0 xt, equal theta of xt. Okay, this is simply what it means. And so there, perhaps we can just write it in a more suggestive form. We are going to write it in the following way, that theta x of t is simply the integral over dy of theta 0 of y times the delta function. So formally, so the average over space times delta of y minus x 0 xt. So this kind of formula is, okay, here it's nice. It is an example of a representation formula which is why, the interesting reason why scalar quantities are interesting to consider. We will see that later. And in particular, when we'll discuss a bit later in the course, what happens of this representation formula when we add forcing and dissipation. Okay. For the case where kappa is not 0 and f is not 0, see later. Okay, and this will be interesting. So now that we have this representation, perhaps we can show some pictures of what a scalar look like. There are some very nice videos. So obviously, a scalar quantity, which can be a dye or a temperature, is the way when you can visualize a velocity field. So we have a velocity field. We put a small quantity which does not back react on the field, and that will behave as a scalar. And this is usually the way, one of the only way that we have to measure quantities related to the fluid, to the underlying fluid field. And so this is an example. So this is an example where the underlying equation is the Navier-Stokes equation, and the passive scalar can be. So there is some marker here, and the colors here can be interpreted as the passive scalar. So this is a video that was it's a historical video, one that was made by
During the forward motion, the boundary of the
Taylor.
fluid follows the path determined at each instant by the motion of the wall. At these very low Reynolds numbers, particles within the fluid move when the boundary moves, and they stop when it stops. During the reversed motion, the boundary of the fluid retraces exactly the path it followed during its forward motion, and the particles return to their original position.
So in this video, the color, okay, so which indicates whether it's black or white at a certain position of the fluid, it behaves as a passive scalar. It does not influence the velocity field. Okay. Other examples are perhaps more can be a bit more spectacular. So typically, one way that has been used to make some visualization of a velocity field in the past and even currently is to use the so-called Schlieren technique. Basically, it's a technique where what is seen on the camera is something which relates to a variation of the refractive index of the air. So typically, a small variation of the temperature. And the variation of the temperature will appear in terms of different color patterns in the camera. And those color patterns can also be thought as a passive scalar. And so this is the example. I'll just put the video. Very nice also. I don't know if there is sound. So here the color patterns that we see, which represents a small variation of the temperature of the ambient air, is a quantity which is a passive scalar as well. Yes.
So these passive scalars are basically just ways for us to keep track of Lagrange markers.
Exactly. And so in this interpretation, it's pretty much straightforward because there is okay. So we have deterministic trajectories. In passive scalar, exactly tell you where the hot temperature. So in this case, you start with something that was a bit hot, okay, and then the different color. The hot particle will stay hot, and then we can track it with those kind of techniques. This is only that. And so, evidently, one may think that anything which relates to the passive scalar, will have a strong tie to the underlying velocity field. So this is what we are going to discuss. So that was an example. And so the interesting thing is about those equations is because they are so tied to the underlying velocity field that they share many properties with it. And this we are going to discuss. So in particular, we are ultimately interested in the case where the underlying fluid will solve the either the Euler or the Navier-Stokes. And so this will lead us to define basically two classes of scalar and to study their properties. So Euler theta okay, it's simply a scalar, it's a passive scalar. Plus let's put it 0. Let's solve, which has no right inside, and for which the underlying velocity field solves the Euler equation. Okay? And we can also define, of course, the ns theta scalar. A case where we will be interested in studying the joint pair of equation d theta plus u dot theta here in the presence of forcing participation. Sorry, with G. With dtu plus u dot u plus gradient of p equals something which is also sustained by viscosity and forcing. Okay, two categories of passive scalar, very natural. And first, let's begin with this guy, and let's discuss some of the properties of this guy, to make an analogy with the underlying velocity field, and in particular. We can discuss the presence of conservation laws. So the Euler theta system preserves naturally the kinetic energy, of course, because the scalar does not back react on the velocity field. The kinetic energy simply the integral of motion of u dx, 1/2 over the domain. Okay, so see lecture 1. And also preserve what we refer to as the scalar, either the scalar variance or the scalar energy, which we will write, say, G here. Is the integral of theta square dx. Okay. The proof is quite straightforward. The proof is quite straightforward, but requires, of course, incompressibility of the velocity field. And it is simply to write that d over dt of G is theta d theta of dx is minus theta di of ui theta. Sorry, I'm going to put ui di theta dx. I use an Einstein notation. This is minus ui di theta square over 2. And this is minus di of ui theta square over 2 by incompressibility. So we have this is by incompressibility. And this is 0 because of the periodic boundary conditions. Okay, yeah?
Should any function of theta be conserved?
Thank you for this remark. Exactly. So in fact, any functional, say g index f with the integral of f of theta dx is preserved. A demonstration, check. Indeed, it is a transport equation. So in a sense, this equation really resembles some equations that we've already seen. It really resembles, for instance, the vorticity equation in 2D. It also resembles the Burger's equation. The only difference is that in the vorticity equation, theta was related to the velocity field by rotational. In the Burger's equation, theta was the velocity itself. So it was those two equations can be thought of as not passive but active scalar. So those are transport equation. The passive scalar is very simple in that case because it's very does not back react. Very easy. And since it doesn't back react, it also transports, those equations transport a lot of the initial properties. So we discuss conservation laws. We can discuss symmetries as well, which is going to be useful. Symmetries. The Euler theta. So the Euler theta is invariant under essentially the same symmetries as the NS equation. So under the same symmetries as the Euler equation. This means that, in particular, we just pay attention to the one which will play a role in this in this business. So the translation symmetry, the time symmetry, the time translation, sorry. The rotation x u gives ox ou for all a given rotational matrix, and the scaling symmetry, which is x t u theta, which gives lambda x, lambda to the power 1 minus ht, lambda h u, and so this is the regular Navier-Stokes, and the only difference, which comes from the linearity of the equation, is that the scalar can change as it wants. So it's you have lambda h, and we can write lambda to the power h theta. Okay. Maybe it's a bit confusing. Let's write just gamma theta. Okay. So it means where basically in that case h is take it positive to be simple, and gamma is positive, and they are independent. Okay. And so this is the only difference between the symmetries of the initial Euler system and the Euler theta system. So demonstration, check. Just take the discussion of lecture 1 and just verify that those symmetries hold. It's a straightforward exercise in manipulation of PDE. And so in this sense, we have already a lot of similarities between the Euler and the Euler theta system. And of course, as discussed previously, Euler and Navier-Stokes are two different beasts. So what is of interest for us, and in particular with the idea of describing turbulence, is not so much the Euler, but the Navier-Stokes. And in that respect, we can just comment a little bit about the Navier-Stokes form of those scalar equations. So NS theta system, which will be referred to a dimensional NS theta system. Let's put, let's say, non-dimensional form. So we take, again, the NS theta, which is dtu plus u grad u plus gradient p equal nu application of u plus forcing. Okay, and d theta plus u dot theta equal kappa theta plus g. Then upon introducing some typical length scale, upon introducing the typical scales, so that basically U0, T0, L0. Think about the same way that we were thinking in the first course of the flow around an obstacle. Here we can Here we can think of a flow about a quantity like an aspirin, something which is going to where some small particles are going to detach. Okay, and this will represent the passive scalar. The number of particles in the flow will represent passive scalar, and so this will have a certain size L0, and the fluid will be U0 here. And so if we introduce those time scales, then the NS rescale, NS theta rescales into, I will write it there. dt u prime plus u prime plus prime p prime equals 1 over Reynolds times theta prime u prime plus f prime, and d t prime theta prime plus u prime of theta prime equals 1 over another number, which is which we call Peclet, of delta prime theta prime plus u prime, where essentially u prime is u over u0, t prime is t over t0, x prime is x over x0, etc. And the Reynolds number is u0, L0 over nu. And the Peclet number is U0 L0 over kappa. So the interesting thing is that in this Peclet, in the Peclet number, what intervenes, and this is due to the linearity of this equation, are characteristics of the velocity field. Okay? And in particular, observe, it is traditional to introduce essentially the ratio of those two quantities, so that the Peclet, it's U0 L0 over nu times nu over kappa. Okay, so this is Reynolds. So this is Reynolds. And this is the Schmidt. Is with a D or with a T? Schmidt number. So and this is, sorry, Peclet number. Peclet. Okay. So the interpretation is the following. So we can quite naturally, the Peclet measures the strength of the diffusive term related to the advection due to the underlying velocity field. And heuristically, Peclet heuristics, Peclet, it's the ratio of two time scales. So it's in particular U0 over L0 times L0 square over kappa. So this has the dimension of a time, 2 kappa, and this has the dimension also of 1 over tau u. Let's put it to 0. And this is the advection time, and this is the diffusion time. Okay, and so we have this following picture. So when the diffusion time is very small, so if we take this picture again, so we have this thing. So if the diffusion time is very small, so that if Peclet is very small, then my small molecules of aspirin are going to diffuse radially. And we can have some upstream motion. Okay. So radial dispersion. Radial dispersion. And by contrast, if we take the opposite limit, then what's going to happen is that if Peclet is greater than 1, then this guy is very large. It takes a long time to diffuse. So this means that the concentration will essentially diffuse in the wake of the cylinder. Okay, so in that case, there is no diffusion, no radial dispersion, and this means that there is no upstream motion. Okay. And so we will discuss later, after the break, so how we should scale Peclet and Reynolds in order to observe interesting phenomena, and to anticipate a very reasonable choice is to take this ratio equal to 1, so that balance of diffusive force due to molecular motion are the same as the molecular motion happening on the scalar, so which makes sense if we have in mind the kinetic theory of of gas, where essentially those two terms represent contribution from the same phenomena at the microscopic level. And so with this in mind, let us make a break until 4. All right, so now that we have covered some basics on what those equations are, the scalar equation, let us talk about the subject that we care about, today at least, which is the subject of scalar turbulence. Which essentially we will have a new kappa. We'll discuss that later. So we have already seen some example of scalar turbulence, which were the videos that we were discussing, we were watching before. Let's put them again because they are quite nice actually. In this case, where the Schlieren, we'll see an example of forced scalar turbulence when the dryer comes. This is turbulence. With this small intermission, let's just so the subject of scalar turbulence is basically the subject of understanding what's happening when nu and kappa goes to 0. Okay, and basically we can make exactly the same remarks that we did for the Navier-Stokes. So that if we take a look at passive scalar turbulence, that consists in solving the NS theta equation with f g non-zero. This is what we see. So this is taken from the review of Varaft. So those are experimental signals. Top is the velocity field taken at one point. Second line is the scalar field, same point, and then the derivative. And clearly, what you see is that those signal looks random, so the same as both for u, as we discussed, but also for theta. The patterns are a bit different related to whether we are looking at the u or the derivative with respect to time. Those are cuts of the scalar where forget about the slope, which relates to forcing, but essentially the simulation which is done by using numerics, where at each point, at a different point, so you have we have a gradient here of theta, and we measure the temperature at a different field, along different line, and so we see something which is very much irregular. And perhaps this numerics is what tell you what scalar turbulence is about. It's so this was obtained with the same kind of Reynolds number and a Schmidt equal to 1. And so the color codes the intensity of the scalar. And well, in the same way that we describe turbulence as some kind of organized mess, the scalar when in those regimes, also some kind of organized mess, with the exception that it's a scalar quantity. So maybe we can hope to describe it in a simpler fashion. And the question is basically, how does this random organization relate to the organization of the velocity field? And of course, the question is there some kind of self-similarity in this picture? So in order to address this question, what we can do is to extend the K41 framework. Let us extend the K41 framework to the case of the NS theta equation, to the NS theta equation. In order to do that, so we are going to formulate the K41 framework in a stochastic way, in the same way that we did in last week. And so we are going to define a turbulent scalar, that we may call a new kappa hist, okay, which will be a stochastic process. So u theta will be a stochastic process. With a joint law of u theta, which is something that we are going to call mu, indexed by nu and kappa, so that averages with respect to this measure, we should write nu kappa, or we will also forget those indices, will be simply the integral of any function of u and theta d mu nu kappa of omega. We have omega is underlying probability space. Space. And we will ask the following conditions, such that some number of conditions are satisfied. Essentially, that for each realization, T give u theta u of T, theta of T solves NS theta, almost surely. And that, in terms of the stochastic process, u theta is stationary isotropic, and last one, homogeneous. Okay, and we are going to require that a certain number of correlation lengths, the correlation length, the correlation length, so the following correlation lengths are finite. So I will basically introduce 4 correlation lengths. Okay, one for each, one for the scalar forcing, one for the velocity forcing, etc., etc. And just to reminder. If phi is a stochastic process. Here, phi of x is in R3. I will define the correlation length, which will be L subindex phi, which will be the integral for x smaller than r, the limit of r goes to 0, of phi of x dx, okay, divided by something so that this has dimension of a length. So I need to divide it by phi 0, and I need to take the power cube here. Okay. So I want the eta cube, theta cube, L cube, and L eta cube obtained by putting phi equals, so for this one, for example, so this one will relate to the gradient. So this one will relate to the gradient, so it will be delta u of 0, delta u of x, average. Okay. This one will relate to the gradient of the scalar, delta theta of 0, delta theta of x. And those two will be related to the correlation length of the forcing. So the first one will be u0 times f bar of x. And the second one will be theta 0 times g bar of x. In the formula, okay. And here I just need to define what is g bar and f bar. So it's exactly the same thing as last week. Essentially, where f bar of x is 1/2 of f of x plus f of minus x, and g bar of x is 1/2 of g of x plus g of minus x. So this long definition simply means that I want to define what I would call a turbulent scalar at finite viscosity and finite diffusivity. And what I will say is that I assume that it is a certain stochastic process defined by two variables, or four if we take the three components associated to the velocity field and the one component associated to the scalar. The only requirement, so I imagine this stochastic process as an underlying law. And the hypothesis that I make is that this law is invariant under time translation. Statistically, it's isotropic and homogeneous, invariant under rotation, invariant under space translation. And that basically, the connection to the NS theta equation is that, well, any realization of this process solves the NS theta equation. And then basically, in order to have something which looks like what we are going to see, we need to introduce some correlation length related to the gradient of each equation and the forcing of each equation. Okay, and here we are going to assume two Okay, let's assume the following relation between those lengths. That basically I want eta equal eta theta and L equal L theta. To simplify, basically, I will assume that the correlation length of the scalar is the same as the correlation length of the velocity field. Same that the correlation length, the correlation length of the gradient of the scalar is the same as the correlation length of the gradient of the velocity field, which, in fact, reflects this hypothesis that we are dealing with the same mechanism at small scale. And so under for those kind of process, this will allow me to perhaps make clearer an aspect which was a bit unclear last time. So for U theta, a turbulent nu kappa hist process. The following relation holds. And this relation is basically will be the counterpart of the Kerman-Horwath Monin equation that we wrote the last time. And it is simply an equation which will say that a certain quantity, I will call it D, which depends on U and theta, and a certain separation, X, is equal to minus U. So this is equal to the correlation of the scalar. So this is grad theta of X plus correlation of the injection. So theta 0 G bar of X. And those average are the average with respect to the underlying measure. So we can put nu kappa, even if it's a bit heavy. So this holds where this guy is something that is well known, can be computed as du theta of X. It's minus 1/4 of the gradient with respect to X, the divergence with respect to X, of a certain correlation between the scalar and the velocity field. This correlation is this one. Delta theta square of X, delta U of X. Okay, so this is a divergence, and this guy is a vector. This is okay, and this guy is a scalar. And so when we have that, so here X is in R cube. It's a separation. And delta U and delta theta are the same quantities as the one we defined, analogous to quantities we defined the past week, in the sense that delta U of X, it's U of X at time t equals 0, say, minus U of 0 at time t equals 0. And delta theta of X, it's theta of X t equals 0 minus theta 0 t equals 0. Okay, and this is also sometimes referred as the Karman-Horwath-Bonin relation for the scalar, but it's also one other name attached to it. It's a Yaglom. We call it a Yaglom relation here. Okay, so to see what it means, we are going to do the same thing as last week. We are going to average this guy on a small ball of radius, a given observation scale. This will give us the scale-by-scale budget. So let's call it Y. Average Y on X smaller than observation scale L. So in order to do that, let's just make a remark. Observation. If phi is this kind of stochastic process with a certain length L phi, for phi such that this holds, then the average of phi for x smaller than L, it is nothing but the 1 over 4/3 of PL cube, okay, times the integral for x smaller than L of phi of x dx. Okay, and so there are two cases. So if L is very small with respect to this correlation length, then this we can approximate by the value at 0. So this is phi 0 times the ball, so 4/3 of PL cube over 4/3 of PL cube, and just the value at 0. And on the contrary, if L is very large with respect to the correlation length, then this becomes, we keep this guy here, and this guy will become essentially, will converge towards the limiting value. It will be the value at 0 times the correlation length. Okay? It will be phi of 0 times L phi of cube, which is nothing but up to a geometric factor, which we are going to write 3 over 4 pi of L phi over L cube times phi 0. So basically, there are two cases. If we are very small compared to the correlation length, we pick up the value at 0. If we are very far or very large compared to the correlation length, we pick up the value at 0, but modified by a factor, the correlation length divided by the length cube. This is the main observation. And so the consequence consequence. So let us write epsilon L is equal to this guy average over the scale, okay? And then for L, which is very large with respect to eta theta and very small compared to the L, what we have is that epsilon L is equal to the average of those guys on the respective scale. So one is the first one. So we have L, which is very large compared to eta theta. So this relates to this one. So this means that we are looking at this formula here. Okay. So this means that we have minus nu grad theta of 0 square okay plus, so this we have a factor eta over L, eta over L cube, times this 3 over 4 pi. Okay, plus, in this case, we have just the correlation of the scalar theta 0 bar of 0. Simply, we apply this formula for the second one. And for eta greater than L, then we have the two formula which apply. We have epsilon of L, which is 3 over 4 pi of theta 0 bar of 0 L over L cube minus mu grad theta square eta over L cube. Okay, and finally the last one, which is L, which is very small compared to the theta. In that case, we can show that epsilon L is 0, and this is exactly the balance between the gradient of theta square plus theta 0 G0. In other words, okay. So if we call, okay. So let us call epsilon theta, which is the injected scalar, which we should call theta 0 G bar 0. Then we have that epsilon theta is nu right theta square. That epsilon L is essentially epsilon theta 1 minus eta cube over L cube is nothing as epsilon theta for L, which is greater than eta theta is greater than L, and epsilon L equals 0 for L greater than L. Okay, so this means that this range here is the inertial range for the scalar. To be fully exhaustive, we need to also specify what epsilon L is in a general way. And so if we take this guy and replace it by this expression, so on the other hand, epsilon of L, so it's 1 over 4/3 of PL cube times the integral for x squared than L of this guy of the divergence with respect to x of minus 1/4 of delta theta squared delta u. So this is we have the integral over volume of the divergence. So this will be simply, so this 1/4 will go there. So minus 1/4 of 1/4 times p L cube. And then we are going to transform this to a surface integral, which will, if we express it as the mean, is nothing but 4pl squared times the delta theta squared delta u for x equal L. So if we we are left with minus 3/4 of L, or minus 3 over 4L of delta theta squared delta u parallel of x equal L with delta u parallel is delta u dot pointing in the direction of the vector x over x. Okay. So this means that in the inertial range, we expect that this quantity behaves as a linear function of L. Consequence. Consequence. In the inertial range, we expect that delta theta squared delta u parallel x equal L equal to minus 4/3 equivalent of epsilon theta L for L, which is smaller than the integral scale and bigger than the correlation time of either, and this is also the gradient or the velocity. So this is an exact relation. And one can see that this exact relation intertwines the scalar and the velocity, which is unfortunate, but which is to be expected because the scalar depends on the underlying velocity field. But we can still explore, suppose that the K41 framework was to hold. What would it imply for the increments? Now, hypothesis. So is the scalar statistically scale invariant? So suppose there is okay, we know that it's not very true, but okay, that there is a monofactorial scaling for the velocity, so there is H0 such that basically delta u parallel is at scale L is equivalent in law to L to the power H delta u parallel at 1. And we have seen that K41 impose H equal 1/3. Then, okay, voilà. Okay. And there is, so you suppose that there is an H, so that's my velocity field is scale invariant, and there is an H theta, such that delta theta L is also equivalent in law to L H prime delta theta of 1. Then, basically the relation and the scale by scale budget imposes essentially that twice 2h prime plus h equal 1. So if h equal 1/3, h prime equal 1/3 as well. Okay? So if we have monofactorial scaling, so if we have so if Kolmogorov theory applies, and that we have also we assume that there is a single exponent describing the statistics of the scalar, then this exponent has to be the same for the scalar and for the velocity field. Okay. And this, so this in particular imposes so this implies that delta any power, say, of delta theta to the power p behaves as a certain function, which is delta theta 1 to the power p times L to the power p over 3. Okay, and so again, this is true. And so to verify this, so this we can write is L to the power psi p over times this function with psi p equal the log of delta theta p divided by the log of L. The limit as L goes to 0 equal p over 3. So basically, so we expect the same statistics as the NS turbulence. And we'll say, okay, it's not totally normal because after all, the scalar is just tracing the field. So okay, we have a complicated relation here, but in fact, there is nothing to expect from this poor scalar equation, which is just totally driven by this velocity field. So that basically, okay, we should see exactly the same thing. Is this the case? Is this the case? Those are the numerics. And this is the behavior of the structure function. So the scalar intermittency. So those structure functions, or the behavior of those quantities, were measured in a series of both experiments and numerics. The data here was done by Ayer and collaborator. You can see the date is very, very recent. So this means that it's still an unsettled question. And basically, the different points here are different campaigns and different Reynolds number, which means different values for this guy here. Okay. Other experiments, this condition is satisfied more or less. And okay, I will, I think, comment on this line here, which is which represents the red line represents the latest numerical results by this team. And just also to mention, this line here is the Kolmogorov prediction, the black line. It's the P over 3 prediction, which is written here. Okay. And what we see is that in this picture, it seems that the intermittency observations the intermittency of the scalar seems more pronounced than the intermittency of Navier-Stokes. In particular, so breaking of scale invariance for the scalar is more pronounced than for Navier-Stokes. And in particular, one can realize that apparently it may be conceived that psi p of theta goes to a certain value constant, say psi star of, psi p of theta goes to a certain value, which is finite as p goes to infinity. This is what you see here on this slide. Apparently, maybe something like approximately 1.2, but we don't really care about this value. Can also go down, yeah, indeed. But the question is, what does it mean, and whether it actually, even if it goes down, it has an interesting consequence for the what the scalar field looks like. So this is what I want to comment now. So what does that mean? What does that mean? What does that mean? Knowing that, well, this is those quantities are quantities which are averaged over both the velocity field and the scalar, so those are complicated quantities. But it's not so clear how to interpret those kind of average and average quantities. It's not so clear, but fortunately for us, there is a very powerful theorem which is due again to Kolmogorov, which is a theorem which is related to stochastic processes. So I will just, so here I need to use my nose to quote it correctly. So Kolmogorov continuity theorem. So basically, the hypotheses are the following. You take xt of stochastic processes with a continuous path, almost surely. And you assume that there is alpha and beta greater than 0, such that for all t, there is a certain constant which depends on time, such that x of t minus x of s power beta is smaller than c of t minus s power 1 plus alpha. For all st in 0t. Okay, so you assume that you have an average behavior which tells you that you have some kind of Holder regularity. Okay, and then this implies that for each gamma in in 0 alpha over beta, t is greater than 0 and almost every realization, there is a constant. There is a constant k, which depends on everything. T, etc. Gamma, such that xt omega minus x omega without the brackets is smaller then k to the power t minus s gamma. So basically, it's a theorem which tells you something about the properties of the realization given the properties of the average. Okay? So for almost every realization here, without any average to be taken, if this is true, then so here we can think of this as a field. The field will have certain regularity, and this regularity is prescribed by this kind of exponent. So let us see what this implies for our case. So now, suppose now that application suppose that this holds. Take beta is equal to p, and alpha is equal to psi p minus 1. Okay? Then if we use this thing, then alpha over beta is equal to psi p minus 1 over p. And so if psi p goes to constant, this means that this goes to 0 as p goes to infinity. And the same would hold true if basically if another situation would be that psi p does not converge toward a constant, but it just grows slower than something linear. And the same conclusion would hold true. And this means, this implies that this suggests that realization of the scalar field are, I put this between quotes, 0 Holder continuous. Okay? Meaning they develop shocks. And this actually can be, this is very consistent with the observation. Well, you see indeed that in this picture, you have some large patches where the scalar is very red. There are other where it's very yellow. And basically the interface between the two is very sharp. And it's so sharp that it can be a shock in this sense. It could it's very likely that in the limit when you let everything go to 0, even kappa, this could be indeed a shock. And this is, in the literature, this is known as a cliff structure that you can see on those cuts. So the fact that you have some huge variation here, poof, is something like at some point the statistical signature of those events could be that essentially the zeta p here do not grow linearly at large time, or it will grow slower than linearly, so this thing holds true. And this is very, very different than what you see in the Navier-Stokes, where we don't believe that there is shock. And so this allows to formulate perhaps the interesting question. How does scalar intermittency ties to NS intermittency? Sorry?
That the people goes to constant, then there are shocks.
If there is, sorry.
If
Yeah. Yeah, well, because of well, there are short, in the sense that it has zero order continuity. If this is your definition. It's worse, but if you apply this theorem, you get the same conclusion. Yeah, the same conclusion. In fact, even if the zeta p would not grow or would not converge to a constant, say that they grow logarithmically with p, then this ratio will still go to 0, and so the same conclusion will hold, except that they will be harder to see probably. And so this is an. So this, I think, this argument tells you that the intermittency in scalar turbulence is very different than what you see in Navier-Stokes, and that as such, the question on what is the tie between those two objects is an interesting question and not a trivial one. And to address this question further, I give you a rendezvous tomorrow.